And welcome, Mindsetters, to this session of Learn Extra Live for Grade 10 Physical Science. Hope you guys are ready. We've got some experiments going, so you better stay tuned. Today, it's me, Ty, and Tracy taking us for today's session. Tracy,
Thanks,
how are
Ty.
you?
I'm well, very well. How are you?
I'm good. It's been a long day, but you know what? We have to truck on.
We have to, and there's plenty to keep us entertained today. So, seriously, grade 10s, get those exam pads out, be taking notes. And I know there's a notes link on the page.
Yes, Mindsetters, I've already posted that up, so you must go check out my latest post. That will have the links to the actual new, updated Mindset page and your notes. So make sure you follow along. But then, what are we doing today, so they know?
Well, Ty, we're looking into the idea of states of matter and kinetic molecular theory. So solids, liquids, and gases, how they relate, and the theory that links into all of those things, and particularly in terms of change of phase, so like freezing and melting and boiling points and all things like that. So a bit of a recap on last week, but key concepts that you grade 10s really need to know. It's a fundamental section.
All right, awesome. So while you make your way across the board, I need to chat to these guys, just have a little personal time. So Mindsetters, I always say, okay, well, now you guys are grade 9's gone into grade 10, so you guys are no longer grade. Anyway, you guys know that. So, Mindsetters, what you guys need to do is make sure you get on the page, www.facebook.com/learn extra. Chat to me, let me know what you guys are thinking, talk to me so we can help you. I cannot read your mind through the screen, so you have to help me out. On top of that, do not forget, you guys need to also visit www.mindset.co.za/learn/extra/live. So you can get access to our shows, our schedules, and then you can also get access to our notes. Well, your notes, because you guys asked for them, so we're like, you know what, let's actually help them out and find them a link. So now that's all out of the way, we have a session to do, so make sure you stay tuned and get chatting to me. But for now, Tracy, take it away.
Thanks, Ty. So, grade 10s, we're starting with states of matter and kinetic molecular theory, and as I said, it's a fundamental section of work you really need to know. Let's turn and see what we're going to be focusing on today. In this lesson, we will identify different states of matter, solid, liquid, and gas, revise the processes required to change from solid to liquid and then to gas, explain why matter exists in different states by using the kinetic molecular theory, and introduce the concept of intermolecular forces. And intermolecular forces would be the forces between molecules. Very, very important. This is going to be a concept that will take you right the way through your physical science course. So let's get into it. The key concepts, we're looking at states of matter. There are 3 states of matter. I know that you know them. They would be solid, liquid, and gas. What is a solid? A solid is a form of matter where the substance has a fixed shape and volume. Now I'm thinking about a little block of ice, right? Water in a solid state. Now I know you know water as being a liquid as well, because it's a liquid at room temperature, and within our everyday lives we use water to wash, we use water to cook with, and water can be in a solid state as well. And I want you to think that all matter can be in solid, liquid, or gas phases. So solid is a form of matter where the substance has a fixed shape and volume. It takes up a certain, always has a significant shape, fixed shape, and then it will take up a specific volume, and we could look into densities and things like that. What is a liquid? Well, a liquid is a form of matter where the substance has a fixed volume, but takes the shape of the container in which it is placed, takes on the shape of the container. Now I want you to think about having water in a water bottle, and then possibly spilling that water pouring it into a flat Tupperware container or something to that effect. That water would be in a tall glass or in a tall container, and you can pour it out, and it would take the shape of the new container that you've poured it into. But imagine if you had it in that water in a water balloon or something, and you tried to compress it, or even took some water, sucked some water up in a syringe. You can't force it any closer together than it already is. You can do slightly, but it has a fixed volume. It won't go much smaller than that. What about a gas? Well, a gas is a form of matter where the substance has no fixed shape or volume. The gas takes the shape of the container in which it is placed. So it would fill the space. And here you could think about something evaporating and spreading throughout the room. Maybe you can think of some scents or fragrances that they would spread throughout. And one of the ways we can identify that this is happening is through a process called diffusion, that there is a random movement of particles where the particles are free to spread out throughout the room. So we refer to these characteristics of the states of matter as macroscopic properties. Now, I want you to note this word, macroscopic, as opposed to microscopic. Microscopic would be referring to something very, very tiny, which we can't see with the naked eye, whereas macroscopic properties would refer to the big properties that we can see. Okay, so macro being large, macroscopic properties of matter. These also include properties like temperature, pressure, the conductivity. We spoke significantly about conductivity last time, mass, the shape, and the volume. So these are all things we can measure, we can see, we can interact with as we can measure those various large-scale properties that we can usually see with the naked eye. So let's consider changes in the states of matter. A sample of a substance can change state from a solid to a liquid or a gas, and that's critical. Solid to a liquid to a gas, and we can change one to another. So a solid can melt to become a liquid can boil to become a gas, and you can work vice versa, go backwards. So gas can come back to a liquid or liquefy. A liquid can go back to a solid state, and that process would be called freezing. So let's go through each of them. So now we're going solid to a liquid, and I want to just, on these notes, sketch quickly a block of ice, a cube of ice, and it's melting. This process is called melting, so I'm drawing a little puddle around the ice to show that it's melting. The melting point of the substance is a temperature. Recall that we spoke about that last week. It's a specific point, temperature point, at which the process of melting takes place. This is always the same for the same substance. So if you have pure water will melt at a specific temperature. What temperature? 0 degrees Celsius. If we are moving from a liquid to a solid, so water, you now want to get ice blocks. So you pour the water in the little ice cube thing and tray, and you can put it in the freezer, and you're going from liquid water to solid water. This process is called freezing. The freezing point, again, is the temperature at which this process takes place. The last sentence here is critical. The freezing point and the melting point are the same temperature, because if you consider that if we go from a solid to a liquid, or a liquid back to a solid, that temperature at which that change of phase will occur would be the same temperature. So whether it's melting to form a liquid, or whether it's freezing from liquid going back to solid, it will occur at the same temperature. Let's move on, liquids to gases. Liquids can change to a gas at any temperature. Again, I'm now thinking specifically changing, and I'm going to use water as a good example, water changing to a gaseous phase, water vapor. Water can change to a gas at any temperature above the melting point. So if you spill some water from your water bottle, if you spill some water on your desk, it's never going to reach 100 degrees Celsius, and in order to go into the gaseous phase, no, over time, that water will evaporate. So, at any temperature above the melting point, liquids can change to gases. This process is called evaporation. Evaporation takes place at the surface of the liquid. And I'm going to draw a little sketch of a water bubble here, a water droplet, I should say, that's sitting on the desk because I've spilled water on the desk. And these are my little water molecules. I'm just drawing them as quick sketch diagrams. Water molecules on the edge of this water droplet. Now let's have a look. I'm going to slide this down slightly further. Let's have a look at what's happening there. Well, the water molecules right at the edge, and I'm going to draw some more deeper down below, those water molecules at the edge could gain enough energy to leave the surface. Okay, so they can evaporate and leave the surface. They're being held down by the surrounding water particles. So they're being pulled downwards and to the left and to the right and forward and backwards. Obviously, it's three-dimensional. But only the ones at the edge can escape into the atmosphere as a gas. And that is the process of evaporation. This evaporation takes place at the surface of the liquid. Okay? And that is why, if you want something to evaporate faster, you can spread the water out. Okay? Because if we have a greater surface area, then more water molecules would have the opportunity to possibly leave that surface. When a substance gets to a certain temperature and can no longer remain as a liquid, so it's gained enough energy to completely change from a liquid to a gas, and this can be any particles, doesn't have to be at the surface. They can no longer remain a liquid. We observe bubbles forming. And I'm going to draw you down my little picture of a pot. The surface, we've got water going in this pot, and bubbles would form. What's inside those bubbles? I want you to think about this. What would be inside those inside those bubbles in this liquid that are in this water that's bubbling on the stove? It would have to be water vapor, because suddenly hydrogen didn't jump in there, or air didn't jump in there. It's going to be water vapor that has changed from liquid water to water vapor as a gas. Okay? This change from a liquid to a gas is called boiling. The boiling point of liquids is dependent on the atmospheric pressure, because it would depend on how much pressure is at the surface as well. Then if we go to some others that you might be familiar with, gas to a liquid is called condensation. And potentially if you were to hold a piece of a plate or piece of towel over the surface, as you are boiling water over here, what you might find is some of these water droplets, whoopsie, let's take that away. Some of these water droplets could actually evaporate, that have evaporated or have boiled, could cool and condense on the surface, right? Now if I head back, there is another process, usually we refer to solid to gas, is called sublimation. It's skipping the liquid phase, and that very often is linked into the pressure of the surrounding atmosphere. So you could have solid carbon dioxide going straight to a gas if you've got a block of solid carbon dioxide. That's as far as we're going to take it for now. When we come back, we're going to do a quick experiment investigating sublimation. So please do come back and be ready to go. Ta.
Right. So mindsetters, make sure you don't disappear. Do yourselves a favor. Make sure you keep on chatting to me on the page. And by the way, I just want to say, please, if you know any teachers you think are awesome, or any of your older brothers or sisters have gone through into the actual physical science field, please let us know. Get them to talk to us, because we're looking for people who can help build the content for these segments. So make sure you chat to us. Yes, you can email us at content@mindset.co.za. But we'll see you after this break. And welcome back, Mindsetters. Now, I hope you've gone and done whatever you've had to do. Now that you're back, you're refreshed, you're ready, you went and got water, or you went to go drop off your bags, or you went and did whatever you had to. Now you're sitting in front of the TV with your 3 Ps, your pens, pads, and your phones. Because you need to be making notes, because This would be very pointless if you weren't making notes. And then you also need to have your pens because you need a pen to write. But that's besides the point. Now you also need to make sure that you're on your phone. Chat to me. Let me know what you guys are thinking. Also, make sure that you talk to me on the page. It's so important. Also, the Twitter, if that's your thing, just talk to us because we need to make sure that we get to all the things that you need to. But for now, we've got a session to do and an experiment. I'm staying here because I'm not trying to get burnt. So, Tracy, take it away.
Thanks, Ty. What I've got set up here is a small amount of iodine crystals, and I'm heating them with a little spirit burner at the bottom. And what I'm hoping that over time, we'll just have to leave this for a few minutes. What I'm hoping that we should see is some sublimation, so that these solid iodine crystals are going to turn into the gaseous iodine molecules. Okay, and so I'm leaving that. I've got an upturned flask here. And maybe you can slightly see a purple tinge coming to this funnel at the base. But I think we need to wait for a few more minutes before that happens. So I'm going to leave that on, and I'm going to turn across to the board. I think what I might do is just add a few more, because it's always fun to add some more of these. And maybe we might see a slightly more distinct purple color happening. There we are. Just trying to get them all concentrated at one point where the flame is, because I'm trying to heat them and allow that heat, those crystals, to change into the gaseous phase. Let's head across, and we'll leave that going for a few minutes. Let's head across back to the board. What I have here is the kinetic molecular theory, and this kinetic molecular theory specifically is here to help. It's a theory that we've got some evidence to back up. Okay, so in the same way you would have various things of evidence when you're trying to understand something, we have all these pieces of evidence that add together to help make up this theory and support this theory. And one of those pieces of evidence is diffusion. I did mention diffusion earlier. You might have heard of diffusion, and that is where if you were to spray some perfume or some deodorant in the corner of a room, over time, that smell, sure, will become more and more dilute, but it would spread throughout the room because of the random movement of particles, because of the fact that particles are bumping into one another and so will be dispersing throughout the room. Let's continue now as we look at what this theory actually says. So, to explain the existence of the states of matter, let's get my pen going. To show that to explain these macroscopic properties, we're going to focus and zoom in on the microscopic things. We use a microscopic model to explain this. The kinetic theory of matter states that the matter is made up of tiny particles. Now, I want to just look at the word kinetic. Sorry, you've gone down a little too low here. I want to look at what this means. Kinetic. If you think of kinetic energy, you're thinking of the energy the object has because of its movement. If you're thinking of kinetic theory, what we are looking at is the movement. Okay, so it's the kinetic theory of matter, and it states that matter is made up of tiny particles that move all the time. All matter is made up of tiny, invisible particles that are moving. These particles could be atoms, so neutral individual atoms, molecules, as in groups of atoms making up molecules, or ions. And remember, ions, you're looking here at something, a particle with a charge, either positive or negative. Whether matter is made up of solid, liquid, or gas, the particles move. And that is fundamental, that all particles move all the time. The higher the temperature, and this is key, the faster they move. And then lastly, there is a force of attraction between those particles. So we're going to be considering forces between particles. I want us to head back and quickly have a look. I can see some purple vapor over here, and I hope you can too. If I hold this white page up behind it, what you should see is that this iodine crystal has vaporized, has gone into the gaseous phase. Maybe we should say it's boiled, but it's changed into the gaseous phase, and you can kind of see that purple haze that is formed. And if we look very closely, we can even see the little purple crystallization that is taking place on the sides of the funnel, and that is because the funnel is cold. It's not as warm as the base of that beaker, and so the surroundings would take up the energy and allow that to cool back down and crystallize again or solidify. So I'm going to take that off, and we'll head back and look at some of these gas, solid, and liquid phases in terms of what's happening inside each of them. I am going to go through these quite quickly. If we consider the gas phase, the average distance between the particles is very big and is much greater than the distance in liquids or in solids. Because of the big distance, there is very small forces happening. The molecules move all the time, and they move on a much larger scale. Because they collide and change direction, we find random motion, so constant moving all directions. The gas will fill up the whole container that is kept in, and the average kinetic energy is directly proportional to the temperature of the gas. Let's go to the liquid phase. Once again, I'm expecting that you'll be able to go and find these notes, so we're going through them quite quickly. The particles are quite close together, but the force of attraction is smaller than in a solid, but greater than in a gas. The particles have more freedom of movement, so they're able to move than in a solid, but less than in a gas, because the forces of attraction are slightly greater. Liquids can flow, and that's a key word. You can pour a liquid, and the particles are able to move and flow over one another. And again, average kinetic energy is proportional to the temperature. In a solid phase, those particles attract each other strongly, so there's a strong attraction. The particles are arranged in a fixed way. The particles vibrate, so they're still moving, but they're vibrating around fixed points. So they're only moving around fixed points, and that's why a solid would be a specific shape. The particles are arranged in a regular way and form beautiful crystals. We have some very interesting, beautiful crystals that you can investigate. And once again, the average kinetic energy is directly proportional to the temperature. Now, we've gone through that quite quickly, but the reason I want to do that is because I want to show you an animation. This is a PhET animation, and I'm going to start with neon as a solid substance. So here we have the neon atoms as solid. I'm choosing neon because neon has not bonded to anything else. So it's individuals, little atoms, and I want you to watch what happens when I heat it. So I'm heating it up, heating it up, heating it up. Do you recognize that those atoms are moving a lot faster? And let's heat them some more. And now they're able to flow past one another, and that would be a liquid form. Let's heat up even further, and let's watch and see what happens. What we should be able to see is some of them, there we are, going into the gaseous phase, and that would now certainly indicate boiling. Let's change and go back to water, and I'm going to reset, and let's go back to water. Remember, water is one oxygen molecule with two hydrogens, and that's why it has this specific shape. So you can see that oxygen indicated in orange, and the hydrogens indicated by the little white balls as well. And that would be solid, as in solid water, ice. If I heated it up, we should be able to see those particles are able to move over and slide over one another, flow over one another, and so that would be indication of a liquid. Recognize they take the shape of the container they're in. And if I heat it some more, some of those water molecules are able to escape. That one's escaped, and will fill up the entire space. So this would be indicating a gas. let's turn and look at some questions that you could be asked based on this. So, question 1. Draw a sketch. I think I need to just extend this page here. Draw a sketch to represent molecules of a substance undergoing the following changes. So freezing. Before we do that, I want to just jot down what we're talking when we're saying something freezing. Well, it's going from a liquid to a solid. So liquid changing to a solid. And for a liquid, and I'm going to jump back to this animation. I'm going to put up what a liquid would look like. The particles are free to move over one another, but don't have complete freedom to fill the space of the container. So let's see what our sketch could look like. You've got little particles that are free to move, and I'm putting them within a container. Apologize that mine aren't all the same shape or exactly the same size, but they would slide over one another. Maybe not, you could even draw them slightly further apart. A solid that's my little solid block, and you would indicate all those very, very tightly packed particles. If we were to indicate evaporation, and again, I'm jumping back to my animation. We're going from liquid to gas, and I'm going to heat this up, and you should be able to see some of the molecules escaping into the atmosphere or escaping into this rest of this container. So we have evaporation is going to be going from a liquid changing into a gas. And once again, we have those liquid particles. I need to make this page a little longer. Changing into a gas. Again, we've got some liquids there, but a few of them escape into the atmosphere. And then sublimation. Now, sublimation, remember, we've just investigated it. It would be going, and this is answer C, it would be going from a solid changing directly into a gas. So let's draw my solid in that little block, tightly packed, changing into a gas. And so we should have these particles randomly spread throughout the container.
Okay.
I think, Ty, I'm going to call it there. When we come back, I've got quite a few experiments to do, something that you could even try. We're going to be looking at the temperature changes when things melt or when things boil. So a fascinating section. Don't
Awesome.
miss it.
Is that what you get with what is that thing called? That ice, that snow, that ice that actually just turns straight into like vapor. Well, I don't know. Make sure you guys stick around because we're going to be doing a lot more awesome stuff. So do not disappear. Just do yourself a favor. Keep on chatting me on the page. But for now, we'll see you after this break. And welcome back, Mindsetters. Now, right now, I'm just trying to make sure that I don't pass out because this room is smelling very interesting right now. That's because we've got some experiments coming up. So while I'm going to try not to pass out, you guys need to pay attention and make sure you got those notes and you're making notes and you're chatting to me on the page, which is awesome. So I'm going to hand over to Tracy, who's going to continue with the show. Tracy, take it away.
Thanks, Ty. I hope you're not really feeling like you're going to pass out because we haven't got that much going, just a bit of ice and water. What I want to show you here is the inside of this funnel that I had a few minutes ago. And again, I'm just going to put a piece of white paper above behind. So what I'm hoping that you can see is those little tiny crystals of iodine that have formed on the inside of the funnel, just to show that it has solidified again on the cool sides of that funnel. And it's quite nice and sparkly.
Pretty.
If we turn across here, I've got some ice, water, and I want us to have a look at the temperature. The temperature on this, if I read it correctly, is just above freezing. It is at 2 degrees Celsius. Okay, and that is, you can see some very cold water, pretty much stabilized there. And this one I've got quite close to boiling. We've got our flame below, and this one is currently at about 78 degrees Celsius. What I want us to investigate is that we're going to investigate, I'm going to head back to the board. Our investigation, and hopefully you can go through this yourself, is to investigate what happens when ice melts. We're going to start with with some ice in a glass beaker, and we've got that going. Use the thermometer to read the temperature every minute, and then draw a graph of what's happening to the temperature over the course of time. Investigate a second investigation, so that could be our number 1 and number 2. Investigate what happens when boiling water cools, so that would be called a cooling curve. Start with a beaker of boiling water, use a thermometer to read the temperature every minute, and then draw a graph of temperature versus time. So what I want to indicate to you is, before we go back to our beakers, is that in order to do this, you would need to draw up a table. So here I've got the time in minutes, and the reason we would do that, or we could have time in seconds, as long as you don't have both in your table. So I would probably recommend even doing time in seconds and converting all the minutes to seconds, because we want to be able to fill in what is happening with the temperature. Now, as you do that, do not write down, please, don't do that. Don't do this. Maybe let's go with minutes, and I'm going to just pick some numbers. If I have 1 minute, 2 minutes, 3 minutes, 4 minutes, etc. If you were to constantly write down the minutes, you're wasting a lot of time, because the table is telling us that it's time in minutes. So we never, ever write the units within the table. The units are in the heading of the table, not throughout, because it's just a waste of time. The temperature we're measuring in degrees Celsius, and we'll do that in a moment. And we're going to then draw a graph, and I've got the axes there. So let's head back to our table and investigate here. So what have I got? I've got the temperature of this ice. It's currently about 4 or 5 degrees Celsius. And what you should see over time, if we were to leave this going, is that the temperature stays the same. Remember I said it was about 2 degrees, and we haven't got perfect conditions. Oh, no, it's dropping again. Why do you think it would have maybe risen for a few minutes? And the reason is that I wasn't stirring it. So obviously the sides of this container are slightly warmer because they're being surrounded by a warmer room. And we have got, and so the surroundings would be slightly warmer. But if I constantly stir this container and take the reading, there it's gone back to 2, take the reading. This temperature won't change as the ice melts. It all has to undergo a phase change in order to then start raising the temperature again. And the reason for this is because the heat energy that's going in is going into separating or spreading, causing those particles to move away from one another rather than causing them to speed up. So the speeding up, the higher the kinetic energy, means the higher the temperature. And what you should notice here is that this temperature, this ice has melted significantly since I came back to it, and it's still at 2 degrees Celsius. Now, I guess if we had perfect conditions, it might be measuring at 0 degrees Celsius, but it certainly has stayed constant for the amount of time that I have been here, pretty much staying on 2 degrees Celsius. So what I would go and tabulate is after 1 minute, if I was timing this perfectly, which I'm sure you could certainly go and do, it should remain at the same temperature until all the ice is melted. Let's have a look at this one. This hasn't gotten to boiling yet, unfortunately. It was boiling and it's now been cooling. So I think what I'm going to just do is move this one across and heat up this ice slightly. And hopefully what we should see is that it stays at 2 degrees Celsius constantly. Thank you. Hold on, the flame is not really, it's kind of there, but not really doing a huge amount. Let's try and light that flame up some more. It's almost there, but not quite. If I try and heat it again. That's just going, but I don't know how much we can get in terms of heat. What I want you to recognize, though, is our ice has melted, a large amount of the ice has melted, but the temperature, even though the temperature of the room has been much warmer, the temperature of this ice has not changed. It's still 2 degrees Celsius. I'm going to leave that for a few minutes, because what I want to show you next is something quite cool. This is some corn flour or cornstarch, and I've mixed it with water. And what I want you to see is quite some interesting analogies. This corn flour, when mixed with water, is called a polymorph. It's called a polymorph, and what it actually is that it has the properties of both solid and liquid, depending on how much it's mixed. So let's have a quick look there. Can you see that it's not quite liquid, but not quite a solid? Now, I've got a ball attached to this rod, and I've got a beaker of water here, and you can clearly see that water, the ball goes straight through the water as a liquid. Let's turn and try and do the same with this polymorph of corn flour. Did you spot that? It bounces straight off. And the reason for that is because it's got the properties of water, or a liquid, I should say, as it's mixed with water, and the properties of a liquid. Now I'm going to release it slowly, and what I hope you should see is that it does slide down into the mixture, but if I go it quickly, it splashes and bounces off the edge because of this polymorphic property. Okay. Let's see that one more time. I'm just going to shift this water away. Isn't this fun? Let's see if you can see that now. Whereas, let me try and release it and let it go slowly. It's gone straight through, and it's going to be quite gunky to pull it out. There we are. Okay, let's turn back and see what's happening with this ice. It has been heating slightly, but as I mix it again and stir it again, it's actually just risen up to 5. But once again, that is because I was leaving this alone and not stirring it. And once again, the temperature is dropping back down. It's currently now 4, and it's going to get back down to 0 degrees Celsius. Okay, let's turn and see one or two more questions based on this. If I turn to question 2, and this would be what a graph would look like based on the practical we've just been investigating. During an investigation into water and its properties, Precious took some ice cubes. So she started with ice cubes, placed them in a beaker and heated them over a burner. She then took the temperature over regular intervals and drew a graph from these results. The graph is shown below. So let's have a look at what this graph is telling us. We've got a temperature going from A to B. Temperature is on the y-axis. And what I want you to notice, and time is on the x-axis, what I want you to recognize here is when you're asked to draw a graph, always you have the independent variable on the x-axis and the dependent variable on the y-axis. And as you look at this graph, I want you to recognize that there are some horizontal sections, some sections where the temperature is not changing, even though this thing has got energy coming into it. We didn't switch off the Bunsen burner. The Bunsen burner was going continuously, but the temperature leveled off. And that would relate to a phase change, when something is changing from a liquid, or in this case, it's going from a solid to a liquid, and then a liquid to a gas. So these horizontal sections from B to C and A to D are always going to relate to phase changes. And you would have to consider the context of the question in terms of answering these. Very, very important to identify that the temperature does not change when there is a phase change. But that's unfortunately, I think, what we've got time for. Let's go back to an ad break. And Ty, would you take it away?
All right, so mindset is make sure you don't disappear. As I keep saying, okay, fair and fine, you need to go do whatever you need to do. You need to go to the bathroom, you need to go get something to drink, but make sure you come back. That's the important part. And guys, keep on chatting to me. Awesome stuff on the page. I want to say hi to Ompile, Tumpa, Mali, Kotsemang, and Simran. I want to say thank you guys for posting on the page, and keep at it. But for now, we'll see you after this break. And welcome back, Mindsetters. I hope you guys have been enjoying yourselves as much as we have, with all the experiments and so much stuff going on. But yes, we have a session to do, so make sure you're paying attention right now. Pens, pads, phones out. We're going to get on with the show. Tracy, take it away.
Thanks, Ty. Let's continue with this question. So we have a graph of temperature versus time for the heating of ice cubes, and we've got some questions to answer. In terms of an increase in temperature, the forces between particles, so we've got a lot going on here, in terms of is there an increase in temperature? Are there forces going on between molecules? The distance between molecules, the average kinetic energy, I'm just going to write that as EK to indicate the kinetic energy. The phase change, increase in potential energy. Okay, the potential energy is the energy the substances have because of their state. And boiling point, what is happening? Okay, so we're going to be looking at this graph, and we've got lots to explain and lots going on. I want to ask you to study this graph. We've got these labels A, B, C, D, and E, and we are asked initially, what is happening between points A and B? Now, recognize that in terms of answering a question like this, you would probably be asked these in separate steps or to focus on one specific aspect. Okay, so go back and look at your graph. What is happening between A and B? Well, A and B, we can certainly see there's a temperature increase. Would you agree with that? As time goes on, the temperature rises. So let's jot this down. We've got a temperature increase. Okay. What is happening with the forces between molecules? Well, they're not changing that much because it's still in the same phase. The particles will be moving faster, but not much. Well, the distance between molecules, this is going at this point, and I want you to notice that we had identified already B to C is a phase change, D to E is a phase change. So what we started off with A was in what phase? And very often you'll be given a question and you really need to recognize that. So we started with A as a solid. When it's going from B to C, at this point here it is melting, okay, between B to C. The reason for that, we can identify it was a solid, it's changing phase, so it must be melting. And then we've got a liquid here, and at this point it's going to be boiling. Boiling, okay. And so I'm going to jump to the next part, and let's see, we've got the same question, but it's going to ask you for at what's happening at point B, and so you could explain. At point C, you could explain. The last point I'd like to ask is, and I'm jumping towards the end here, because I know, are these phase changes that occur physical changes, or are they chemical changes? And this is a question, is this a chemical reaction? No, it's not. The molecules are just being given energy to move further apart. So it's a physical change, it's not a chemical change, and that's probably one of the fundamental things you would need to recognize as well. I think that's all we've got time for. Ty, let's round it off.
All right. So, to you grade 10s who were grade 9s last year who now have upgraded to grade 10, which is thumbs up for awesome. Now, make sure you guys do not forget to use the resources that we've provided for you. Chat on the page. Part of the rules of being a mindsetter is you have to help each other out. So you help each other out by asking questions, by talking to each other on the page and helping each other out. That's how it works. Then on top of that, do not forget to go to www.mindset.co.za/learn/extra/live so you can get all of our scheduled shows and you can know what we're doing for each session coming up. So make sure you can keep on track. So, for me, this is where I sign off and say thank you very much for joining us and take care.